Hello everyone, welcome to the talk titled Superfast Differential Privacy by myself and Gautam Kamath at the University of Waterloo. I'm a recent graduate from the Department of Computer Science and Mathematics at the University of Waterloo, where I majored in computer science and combinatorics and optimization, and I'm extremely interested in differential privacy, especially in the context of machine learning. So this talk is primarily going to be about how to run fast differentially private machine learning algorithms on modern hardware. And before we really get into the nitty-gritty parts of the talk, I'm sort of going to deliver the punchline as quick as possible. So this talk is really about how there's a lot of competing frameworks that allow you to do individual or access individual gradients, which will show us the crux of the problem for doing DPSGD. And we show that JAX, which is a framework that was developed by some folks at Google, is actually much faster than competing frameworks, and we hope that this encourages people to sort of adopt JAX and use it in order to prototype differentially private machine learning code faster on the GPU, and hopefully it encourages people to also pick it up. So to begin with, we'll start with the definition of differential privacy, and for those of us who have seen this before, this should be a quick primer, but I'm just going to succinctly summarize what the definition is essentially saying. So it says that if we have some neighboring pair of points that are close to one another, x and y, then it's very likely that a randomized algorithm, which we want to show is differentially private, m of x, will output a value or will observe a value that's extremely close to the value that we observe for m of y, where x and y are the 2 points in question. And we also highlighted some of the uses of differential privacy at scale at companies like Apple and Google. So hopefully, if you're interested in sort of how to take differential privacy or differentially private machine learning and push it to production environments, these are great articles that talk about how exactly these companies did it and why it's useful. Now we talk about sort of the workhorse algorithm for both this talk and also in general for deep learning that we've seen so far. So in general, for most deep learning models, the optimizer of choice is a first-order method that's some variation of stochastic gradient descent. And the natural extension to the differentially private world is sort of differentially private stochastic gradient descent. And this is really just adding 2 more steps to the regular SGD algorithm. And the 2 steps are highlighted in red, where we just clip the gradient according to some pre-specified value, and we add some noise where the noise is carefully chosen based on what kind of privacy guarantee that we want to enforce. If you're more interested in in each of these steps in more detail, please refer to the blog post. That's the first link down below. And if you're interested in some of the theoretical guarantees or how this algorithm came about, there's quite a few papers that I've listed down below that are sort of the introductory material to this algorithm. Now we talk about what the core of the problem actually is. So PyTorch and TensorFlow initially had a lot of difficulty in accessing individual gradients, and this is primarily because when deep learning came about first, we wanted to process batches at a time. And there was no reason to extract individual gradients because you would aggregate the loss over your batch and then process the gradient for that loss. However, for differential privacy, if we remember from the algorithm, we wanted to clip each individual gradient, which is different than clipping the average of the gradients. And so we actually require access to the individual gradients. And so I've listed a screenshot down below from one of the core devs of PyTorch, which showed that there was no way to actually access individual gradients in PyTorch. And if you follow the issue that I've linked down below, it also says that it's extremely slow if you'd like to do this, if you're just using vanilla PyTorch. Similarly, there are issues with TensorFlow's runtime, although TensorFlow does have some functions that allow you to vectorize over the batch dimension. So now I've listed some attempts at fast individual gradients because this problem actually was attacked by a lot of papers in the past, and these are some of them that talk about how exactly we can access individual gradients in frameworks like PyTorch or TensorFlow. The commonality to all of these methods is that they all present a way to sort of backpropagate each individual gradient, and then you can post-process it in whichever way you want. And for us, we kind of just want to clip the gradients and then add some noise to it. And these present pretty big speedups over just running each individual example one by one, which one might imagine is extremely slow. Now we move on to JAX, which is a high-performance machine learning library that's built on top of Python. JAX just-in-time compiles your code, or JITs your code, along with uses its own accelerated linear algebra optimizer to optimize your code and give you a kernel that runs extremely fast. JAX's API also resembles NumPy to a large extent, which means that if you're familiar with the deep learning ecosystem in Python, then you're also familiar with JAX's API to a large extent already. In addition to this, JAX also allows you to prototype in pure Python rather than prototyping in a framework or another library. In addition to this, one of JAX's core functions is this function known as vmap, or vectorized map, which allows you to parallelize across your batch dimension, and this essentially allows you to get individual gradients. So if we remember from the previous slides, we required individual gradients and we wanted it to be fast, and JAX gives us both of these things. Now we move on to the state of JAX for differentially private machine learning. Unfortunately, there aren't too many papers in the differentially private machine learning world that actually use JAX. In fact, in a Google Scholar search, we only found 2 papers that actually used JAX in order to run their code. In addition to this, we also see that competing frameworks tend to take a much longer time than JAX to actually run. And this means that a lot of the complaints about differentially private machine learning, which revolve around how much time it takes to prototype the code, are not as good of reasons anymore because JAX presents an extremely good solution to this problem. So we hope that this allows for a wider adoption of JAX, especially in the context of differentially private machine learning and differentially private stochastic gradient descent. We now move on to the experimental results section of the paper, where we compare JAX against the competing frameworks that we've mentioned before in the 2 architectures, which are convolutional neural networks and feed-forward neural networks. In the full version of the paper, we also mention a variety of different architectures and more frameworks to compare against. The model specification for the convolutional neural network is the exact same one that's used in most of the DPSGD tutorials, and it's just a convolutional layer followed by a nonlinearity, followed by max pooling, then a repeat of the same 3, followed by flattening of the output tensor, and then 2 linear layers with a nonlinearity in the middle. And the feed-forward neural network is just the last part of the convolutional neural network. We should also mention that for this talk we only focus on classification. However, in the paper we also look at regression as an additional task that JAX outperforms the rest of the models on. The first plot to look at is the feed-forward neural network, and immediately we see that across all batch sizes, JAX is significantly faster in median runtime than the rest of the libraries. We notice that the median runtime is reported instead of the mean runtime, primarily because JAX's mean runtime is slightly higher as a result of JAX's first epoch taking longer than the rest of JAX's epochs, because in the first epoch, JAX's just-in-time compiler is warming up. We should also mention that median runtimes are not the only metric to look at, and there are other metrics like memory utilization and GPU efficiency, which we also look at in the paper. Now we move on to convolutional neural networks, where we notice that the difference between JAX and competing models is largely exaggerated. The main reason for this is because JAX's XLA compiler allows it to compile certain parts of JAX's code into highly optimized kernels that are extremely fast to run. At its fastest, we notice that JAX is about 5 times faster than the closest competitor, which is Opicus. We also notice these results extend to a variety of different tasks, not limited to convolutional neural networks and feed-forward neural networks, that you can find more information about on the paper. We should mention that we were not the first to discover this behavior, and we're sure that there are experts in the audience who are familiar with JAX's extremely fast runtime for differentially private stochastic gradient descent. However, our search on Google Scholar led us to believe that not too many people knew about this. We're also the first to propose a thorough benchmarking of JAX against a variety of other libraries to show that it is significantly faster on all architectures that we've looked at. We should also mention that we're not any of the core devs of JAX, but we're just people who use it and we're not affiliated with them in any way. In addition to this, the full paper should be available at thesalon.ml/JAX paper. However, if you have any concerns or comments, feel free to ping us on Twitter at bgauthamkamat or at Pranav Subramani. I hope you had a great time at this talk, and hopefully you find JAX useful in research or production environments. Thank you.